we were studying about the solution of a system of linear differential equations, where we saw that there may be two quantities in a system that are interdependent or dependent on one another, and we saw that we used matrices basically and solved the eigenvalue problem in order to find the solution of a system of linear differential equations. We saw the equations basically of this form, where the vector x, the derivative of vector x, was equal to a 2 by 2 matrix in our case, and a vector x, where, if you remember, x was a vector with two functions of time, x1 and x2, and A was a 2 by 2 matrix, and we saw how to find the solution, and that is what x1t is equal to and what x2t is equal to, based on the two linear and differential equations that were homogeneous. So we have just covered the homogeneous case when studying this. In today's lecture and this week basically, we will be looking at something very interesting, that is how to visualize the solution of this equation in matrix form. So how to visualize the solution of this equation. We are going to do this through a diagram, and that diagram that will help us visualize the solution is known as a phase portrait. So basically these lectures would be on phase portraits. By a phase portrait, what is meant actually is that for two parameters or two functions of time, we want to see how they are going to behave in relation to one another. That is, we are going to plot x2 against x1. When we plot x1 only against time, basically we get a function of time where on the x-axis there is t, and here we have x1, and here we have t, and here we have x2. But now we are going to make a plot where we are going to plot how x2 is related to x1, or how would x2 change in relation to x1. This is known as a phase portrait, and this space in which we are we make this visualization is known as a phase space. This is very interesting, and it gives a lot of insight into the way x1 and x2 behave, and you should pay close attention, because the syllabus that we have covered after the second sessional or just before that is going to contain most of the stuff that I am going to put in the final exam. So for example, 50% of final exam would be from week 12 and onwards. So basically, pay close attention. We have sort of built our concepts up till now to be able to solve a little more complicated systems where more than one differential equation would be arising, and there would be more than one parameters that particular differential equation would be dependent upon, or the change in one of the parameters may not only depend only on itself but on some other parameter as well. So basically in real situations where we come up with such equations, it is often very handy that if we can visualize what the solution would look like. So please pay close attention. So in a phase portrait, usually this point, the origin, is known as a fixed point. You can see that at the origin x1 is 0 and x2 is 0 as well. So if we have an initial condition for this equation, if we have an initial condition where x1 is 0 and x2 is 0, and that is the initial condition, then the system is not going to go anywhere and it will stay here, and that is why it is also called an equilibrium point. So if the system from where this equation has been produced has an initial condition 0, 0, it will have a solution 0, 0. It's not going anywhere. So that is why it is a stable, it is a fixed point, it is an equilibrium point, and the system will stay there. However, for other initial conditions, say an initial condition here, what would this mean? So x1 is going to have this value and x2 is going to have this value. Say x1 at 0, t is equal to 0 is going to have some value, this one, and x2 at t is equal to 0 is going to have some value. Then how would the system for this initial condition behave is what we will be going to represent by a trajectory. That trajectory will tell how the values of x1 and x2 will be if the initial condition is this point. Sometimes this the trajectory will go towards the fixed point, sometimes it will go away from the fixed point, and we are going to look at how things will behave in this fashion in this case. So equilibrium point has basically two possibilities. Either it is a stable point or unstable point. When the nearby initial conditions are pulled toward this fixed point, we say it is a stable equilibrium point or fixed point. So let me just for your remembrance write that if all nearby solutions are attracted towards the fixed point, then we say it is a stable one. And if, on the other hand, if they are repelled, then it is known as an unstable point. Sometimes the word node is used. So instead of a fixed point, we can say it is a stable node or an unstable node. And sometimes the equilibrium point is not a node. Instead, it is a saddle point. We will come to that a little later. Just let me remind you that in the solution of this equation, we used to have two eigenvalues and two eigenvectors, and then we would find the solution. So based on the two eigenvalues, we are going to have several cases. So what is the relation between eigenvalues of certain kind and the fixed point? How would the fixed point going to behave is something to be seen. So if the eigenvalues, the values of lambda in this problem, if you remember that A, where A is the 2 by 2 matrix and V the vector, and lambda is a scalar value and V is the same vector, this is an eigenvalue problem. and we can solve for values of lambda first using that determinant of a minus lambda I to be equal to 0 gives the values of eigenvalues, and then using that eigenvalue and this equation we can find these eigenvectors. So basically eigenvalues are what is going to determine the nature of the solution or the phase portraits. So eigenvalues can either be real and distinct. So if the eigenvalues, two eigenvalues are real and both are negative, if you remember, if the eigenvalues are real and both negative, then we are going to have the solution to contain e raised to the power negative something t. So because the solution, both parts of the solution are going to have negative exponents, and a negative exponent minus at is something that is a decaying something. So you can very easily see that the solution is going to decay, and therefore starting from any initial condition for such a system with negative eigenvalues, the fixed point is going to be behaving as a stable node. I hope you understand this. And if the values are real eigenvalues and both are positive, then just because of the same explanation, the exponent then would be positive e raised power something positive t. This will be behaving as an unstable node. And if the eigenvalues are real, but one of them is positive and the other one is negative, then this is known as a saddle point. I will tell you a little later about why it is called a saddle point. A saddle is basically that thing that you put on a horse where the rider sits, and that is known as a saddle. Why this is called a saddle point, I will discuss when I solve an example with such a case. Now, if the eigenvalues are not real, but in fact, instead they are complex, and you know the values would be complex conjugates. But if the real part of the complex conjugate eigenvalues is real, so the real part is negative. Both the real part of both of the eigenvalues is going to be the same, and if it is negative, then we are going to have a stable, not a stable node, but a stable spiral. We will look at this when we solve an example with a spiral case. And if both the eigenvalues are complex but both have real parts to be positive, then we are going to have unstable spiral. So you see, the fixed point can either be a node or a spiral or a saddle point, and can be stable or unstable. So a saddle point is not stable or unstable because by its very nature it is stable in some sense and unstable in some sense. We will look at that. So the spirals basically are some things. So if the trajectory starts from here and goes in some fashion into this saddle point, it is a stable system. If the trajectory is inward, it is stable. If the trajectory is outward, it is unstable. If the trajectory is spirals into the fixed point, it spirals into the fixed point, then it is a spiral fixed point. And the spiral, we will later see that the spiral can be drawn in two ways. Either it will spiral this way or it will spiral this way, clockwise or anti-clockwise. When it is clockwise and when it's counterclockwise, we will look at that. So basically, this is what we are going to cover. We will try to understand how the phase portraits are made and solve the system of linear differential equations, and find the face portraits, in fact be able to draw them. So if you, till this point, if you really wish to learn piece by piece, so instead of covering everything and then doing some examples, if you try to learn piece by piece, you can begin solving these few questions. For example, the question in the exam may be asked like, determine if the fixed points of the following, or a single equation. Here I am giving you several examples of the following systems are nodes. Now the question asks whether they are nodes or not, saddle points, or spirals, and also determine their stability. So what you will be given would be some system of differential equations, two linear ordinary differential equations in two parameters, x1 and x2. Suppose x1 is the change in x1, the rate of change in x1 is minus 3x1 plus square root of 2 x2, and the other one is x2 dot is equal to square root of 2 x1 minus 2 x2. Initial conditions are not relevant here because you just have to find the eigenvalues and look from this table and see what would the fixed point be like. Say x1 dot is equal to x1 plus x2, x2 dot is equal to 4x1 plus x2, x1 dot is equal to minus half x1 plus x2. Don't do all of these, pick any one and try to solve it on your own. If by understanding something you can do one or two problems yourself, that is sufficient proof that basically you have learned and understood the concept, the underlying concept. So with this, basically we can move forward and try to solve an example of our own. I think this video may be flipped upside down, I'm not sure, but let me pause it if in case it is and start a new video.